Hello students, welcome to another video on digital signal processing. My name is Gajanan Tudvekar and in today's video we will be discussing how to design an analog Butterworth filter. The question displayed on your screen reads as design an analog Butterworth filter that has -2 dB passband attenuation at a frequency of 20 radian per second and at least -10 dB stop band attenuation at a frequency of 30 radians per second. So in the question they have given us the passband attenuation -2 dB, stop band attenuation as -10 dB, pass band edge frequency as 20 radian per second and stop band edge frequency as 30 radian per second. So these are the specifications given in the numeric. The next step is we note down the specifications given in the question. One thing to be kept in mind is in the question they had mentioned the passband attenuation as -2 dB, but while solving the numericals we do not take it as -2 dB, we take the passband attenuation as +2 dB. Similarly, the stop band attenuation denoted by alpha s was mentioned in the question as -10 dB, but while solving the numericals, we do not take it as -10 dB, we take it as +10 dB. Apart from this passband and stop band attenuations, passband frequency omega p is given as 20 radian per second and stop band frequency omega s is given as 30 radian per second. So in this step, we have noted down the specifications given in the question. Once we have noted down the specifications, the next step would be to compute order of a filter. And order of a filter is denoted by the term capital N. The formula to compute order of a filter for Butterworth prototype is displayed on the screen. Capital N greater than or equal to log under square root 10 raised to 0.1 multiplied by alpha s. This entire term minus 1 divided by 10 raised to 0.1 alpha p. This entire term minus 1 divided by log of omega s divided by omega p. So this is the formula to compute order of a filter for Butterworth prototype. Once you have noted down the formula to compute the order, the next step would be to substitute the variables in the formula. So in the formula, you have to substitute the values for alpha s, alpha p, omega s, omega p. After substituting these values and simplifying, you will get value of n as 3.37. So as we have mentioned, we have to round off the order to the next higher integer. Therefore, we will be rounding off the order 3.37 to the next higher integer as 4. Therefore, the order n of the filter for the given specification would be 4. Once we have computed the order for a Butterworth filter, next step would be to write the denominator polynomial for the order obtained in the previous step. So the denominator polynomial depends on the order. Suppose if you get order as 1, we write 1 plus s as the denominator polynomial or the denominator for h of s. If you get order as 2, then we write the denominator of h of s as s square plus square root of 2s plus 1. If we get order as 3, we write denominator of h of s as this term, and so on. So basically, the denominator of h of s depends on the order that we obtain, and the denominator of h of s should be taken from this table. Once we have obtained the order for the Butterworth filter, the next step would be to write the transfer function h of s for the Butterworth filter for the obtained order. In this numerical, we have obtained the order n as 4, and from the previous table we have to write the denominator polynomial of h of s for order 4. So this would be the denominator polynomial for a Butterworth filter for order 4. The next step in the numerical is to calculate the value of cutoff frequency omega c. We have the formula to compute the cutoff frequency as omega c equals omega p divided by 10 raised to 0.1 alpha p minus 1, the entire term raised to 1 by 2n. After substituting the values of omega p, alpha p, and n, we get the cutoff frequency omega c as 21.3868 radian per second. Once we have computed the value of cutoff frequency omega c, the next step would be to find the transfer function ha of s. The transfer function h of s obtained in step 3 is for value of cutoff frequency 1 radian per second. But in step 4, we are getting cutoff frequency as 21.386. Therefore, we need to substitute this value of cutoff frequency in h of s to obtain the transfer function ha of s, and this transfer function ha of s will be the transfer function for the given specification. In order to do so, we need to substitute s as s divided by omega c in h of s. Now, in h of s obtained in step 3, we have to substitute s as s divided by 21.3868. Once we do this substitution and simplify, we get the final transfer function for the given specification. Therefore, this would be the final answer for the given numerical.